What I'd like to do in this video is just run through the multiple choice packet of practice questions and sort of just give a brief explanation of each of the answers, hopefully, to sort of help you get a feel for any of the questions that maybe you're still struggling with and have some background on the reasons behind what they are. So just to kind of go through them rather quickly. I don't want to take forever on each question, but we'll try to hit each one and hopefully give you some background on how to solve each of them that you might be stumped with. Feel free, of course, to slide through and get where you need to be in order to get to the answers that you're looking for or the explanations that you're seeking. So on number 1 through 5, in fact, they all use the same information right off the top. Be aware that that's common in multiple choice questions, that there might be, some information that's given that's useful for more than one question, and that you're paying attention to which questions apply to that information and vice versa. Otherwise, you might feel like you're missing information on something, and without that, you would be. So they're talking about formic acid, which I think is the acid that's found in the bites of like red army ants, but that's not all that interesting. The question is talking about a titration, and important in titrations that remember that most of our acid-based titrations in AP chemistry are of monoprotic acids. This is no exception. 1 hydrogen per molecule of acid. And so be thinking about that 1-to-1 ratio. When that's the case, that gives you some options for a quick titration answer, including to use our usual M1V1 equals M2V2 equation. This is the one that we use when we're diluting solutions. It's the molarity and volume of one solution is equal to the molarity and volume of the resulting solution after you've added water to it and diluted it down to make a more diluted solution. It's also useful for acids and bases. So instead of 1s and 2s, if it's a monoprotic acid, 1-to-1 reaction, we can say MAVA equals MBVB. And that's acid and base. And then you can plug in what you need to know or what you do know to find the parts that you're missing. So molarity and volume of the acid, molarity and volume of the base. Molarity of the acid here is 2. And keep it simple in multiple choice. Don't worry about the decimal places so much. The volume is what they're asking us to figure out. So 2 times VA. The molarity of the base is 1. The volume of the base is 20 milliliters. So we're basically here saying 2 times VA equals 20. Divide both sides by 2 and you get 10. So our answer is A. For number 2, at the equivalence point, is the solution acidic, basic, or neutral? That's really important to think about, because then we're talking about acid and base salts. And the key is to be able to look at the acid, the base that you're using the titration and come up with what the salt will be. Remember, in any titration, typically hydroxide and hydrogen are real obvious. They make water together. The hydroxide and the hydrogen do. But what's the other thing that's made? In this case, it's the sodium and then the formate ion that's going to be formed. So that's Na and then CO2H. So that's our sodium formate salt. I'm really asking then, is this a basic salt or an acidic salt, or is it a neutral salt? And then the reasons why. Well, they give us all 3 of those as possible answers: acid, base, and neutral. And they give us 2 reasons why the base is potentially the correct answer. The shortcut in determining these, the short answer is to look at and realize that this is a strong base, and then this is a weak acid. This is why it's really important to know the strong acids and strong bases just off the top of your head. This is a strong base. It's one of our few strong bases. It's not a strong acid, therefore it's a weak acid. And if you look at those just real quick glance, strong base, weak acid, whichever one's stronger, the base, determines the pH or the character of the resulting salt at a quick glance. So because strong base is stronger than weak acid, this is a basic salt. Now that doesn't give me the answer that we're looking for overall, but it does give me 2 choices. I can get rid of these 2. How do we know? How do we show this is a basic salt? How can we prove it? We could write an equation to show the formate ion acting as a conjugate base of our weak acid. Let's look at the 2 choices they give us, though. Basic, it says the only ion present at equilibrium is the conjugate base, and that in fact is the case. Look, our weak acid was the formic acid. The conjugate base out of there is the part that I've circled, CO2H. This is the conjugate base of our original acid. This guy right here, right? This sodium is essentially the conjugate acid of a strong base, and it doesn't have any ability to act as an acid at all because it comes from a strong base. But this choice 2B looks real good to me. It's a basic salt, we know that, and the only ion present in equilibrium is the conjugate base. What other ions might there have been? Well, the hydrogen ion from the original acid could be there, but it's not, because all the hydrogen ions from the original acid have been, the OH, check that again, the OHs from the base have taken care of all the hydrogens from the original acid. So those two ions have canceled each other out, have joined forces to make water, and so those ions really aren't present substantially. The ion that remains is the conjugate base ion. The other choice they give us in C is the higher concentration of the base, and they're kind of alluding to this notion from the beginning of the problem. The base was a 1 molar solution, is the determining factor. That's not a stronger concentration. The acid was actually a 2 molar concentration, so that was the stronger of the two. Not the base. And so C is sort of nonsense. It doesn't even apply. So that part is flawed, and that leaves me with B as my choice. Now, again, you could write the equation. It's not going to ask you to write an equation on a multiple choice problem, but it's nice if you can justify in your head. So just to kind of take one final moment with this, to show how this conjugate base interacts with water and acts as a base, we can put it with water in an equation. It makes OH, and it returns us and gets us back to some molecules of the original acid that was formed. Remember, this is why we started out our study of weak acids and bases by writing equations for the acid or base, and then writing the sort of reverse equation, the hydrolysis equation, for its conjugate acting on water by itself. And so here we can see it acting as a base to form OH ions, and we know it's a basic solution. Number 3, if the formic acid were replaced with a strong acid, such as HCl, at the same concentration, how would that change the volume needed to reach the equivalence point? It's really important for us to remember here that when we see equivalence point, that means that moles of acid are equal to moles of base. That's what the equivalence point means. It doesn't mean the pH is going to be 7. It doesn't mean the pH at the equivalence point is going to be neutral. It means all the acid has been neutralized by base, true. Okay, but there's a conjugate formed a lot of times, like we just saw in our last one, so the pH isn't always neutral. What it does mean, though, all the time at the equivalence point, when we're titrating an acid with a base, is that the moles of acid are equal to the moles of base, especially for a monoprotic acid and a 1-to-1 ratio, like we have in this case. So it's really asking us then, would changing the acid's identity change the moles of acid present? No. Especially because their molarities are the same. It was a 2-molar formic acid, mentioned that before, and now it's a 2-molar hydrochloric acid. If the molarities are the same, and we're using the same volume, which we have to assume we are, or I guess that's what they're asking us, how would that change the volume? Then the volume wouldn't be affected at all. Equal molarity doesn't change the fact then that the moles of acid would remain the same, and the moles of base needed would remain the same as well. So as we go acid-base relationships, be thinking about equivalence point as being the point where moles of acid equals moles of base. The only way to change the volume needed to reach the equivalence point would be to alter the molarity of the solution, because then you're getting more moles for every drop that you add. You're getting more moles of acid at a higher molarity, for example, with every milliliter that you would add. But in this case, since the molarities aren't changing, the volume required wouldn't change, and our answer is D. Changing the strength of the acid will not change the volume needed, because the moles will stay the same. Which would create a good buffer in number 4 when dissolved in formic acid. Remember, a buffer consists of an acid and its conjugate, an acid-base pair. In this case, it's an acid and its conjugate, because what will be the pair in a buffer with formic acid? Its conjugate base as a salt. So if the acid is HCO2H, its conjugate base in this case is the CO2H ion, and you want to find a salt then that contains the CO2H ion, and that's A. So we dissolve sodium formate into water, and we'd have, or rather into formic acid, and we'd have a great buffer, especially if we had equal moles of those things. That would be the ideal buffer. Number 5, the above equation shows the methylamine reaction with water. Gives us a Kb value there. It's small. It's not tiny, but it is small. Remember, with any K values that are in the negative power range, that means that only a partial dissociation has occurred. What does that mean? That means most of our original acid remains the same. Remember how many times we've done these where the amount of the base lost, that X, that negative X, is treated as negligible because it's so small. And so hardly any of the original CH3NH2 methylamine is going to be converted over to this. We are going to have lots of this left, and only little tiny bits of this, of both of our products being produced. Now, not only are we going to have tiny amounts of both of those being produced, but because of this reaction being 1-to-1 to 1-to-1, as most of our reactions are in this unit, these two amounts are going to be equal, right? Because they're going to be formed at the same rate, one OH for every one CH3 NH3 plus ion. So those two are going to be equal at all times. Go down here to your choices and find one of the options where OH ion is equal to CH3 NH3 plus. And in fact, looking at it, there's only one. It's right here. Those two things are shown to be equal. Okay, right here in the last one. Does the rest of that choice hold up? Those two things should be quite a bit less than, okay, the CH3 and H2 that was present. Or as it's written here, the amount of this original stuff is going to be greater than the amount of the products being made. The original amount of methylamine will remain far greater than the products being made. So this works out great as D. Okay, let's go to page 2. Number 6 on page 2. All right, asks us about conductivity. If I give my page 2 to appear for me. Okay, there I got it. Okay, number 6. A 0.1 molar solution of which of the following acids? Stop right there. They're all the same molarity. So the molarity, the concentration of the solution, isn't going to be the factor. So that number really means nothing to us here. Which of these is going to be the best conductor of electricity? That means which of these is going to best form ions? Form the most dissolved ions. That's what that means. So which of these is going to ionize the best? Which forms the most ions? If we look at all 4 of these, they're all acids. But the one that's different than the other is D. D is a strong acid. Strong acids dissociate 100%. So strong acids turn 100% in this case into hydrogen ion, and for nitric acid, nitrate ion. 100%. You're going to get tons and tons of those ions in a sample of nitric acid. With the other 3, they're all weak acids, so they're only going to partially dissociate. You're going to get a far smaller number of the dissolved ions when those acids are presented with water. And so you're not going to get as many conductive particles, those ions that can do it. More ions, better conductor. All things being equal with their molarity, then it comes down to their character and which of those is most soluble or has the greatest solubility. In that case, we're looking for the strong acid. Great strategy there. When you're asked a question like that, and it's not necessarily this one, but a future question, if you're presented with a question that you're not sure like how to even start, in that case, look for something that sets one of the 4 apart from the others in some way that you are confident about. In this case, that one's a strong acid. That's all I know. But nitric acid is a strong acid, and run with it. Because if you don't have an answer, then pick something and go. Don't spend time on a multiple choice question on a real exam situation more than you can afford to spend. All right, number 7. I think on this one we mentioned in class, in case you didn't get it, we did have a typo on this one. So the H on choice C, H2, C2H3O2, that little 2 there, that's first 2 doesn't actually belong. So this little 2 shouldn't be here. That's a typo in the original. But in any case, that is a hint, I guess I would give away that letter C is going to be our correct answer. But how do we know that? How do we recognize that that's the case? Remember, a buffered solution is one in which we've reached or near the half equivalence point for that acid. So if we're making an acid in a titration here, if we think about an acid titration, all 4 of these being weak acids, we'd get a curve of something like this. And at the equivalence point, we're here. At the half equivalence point, we're somewhere over here. And the buffer region, as we're talking about here, the buffered solution, it's going to be somewhere around that buffered halfway at the half equivalence point. They're suggesting we want something that would give us a pH of 5 at that moment. So if I go to my graph, a pH of 5 over here, approximately 5 on my pH, okay, would mean that I want something that at the half equivalence point has a pH of around 5. And remember, at the half equivalence point, pH is equal to pKa of the acid. Okay. So for a pH equal to pKa, Remember those relationships, pH equal to pKa at that half equivalence point. That's an important fact that's going to show up at some point on every full-sized exam that you'll do. Okay? And it'll certainly be part of your exam on this topic. So if the pH equals the pKa at that point, and we're looking for a pH of 5, we're looking for a pKa of 5. If we want pH of 5, we want a pKa of 5. And remember, pKa is simply the inverse log of Ka. That's where we go to mental math skills. That means you're going to want a Ka value that's in the neighborhood of 10 to the negative 5. pKa of something that's a Ka of 10 to the negative 5, rather inverse log. Sorry, I jotted my line out there. Inverse log of Ka. If we want the inverse log then of about 10 to the negative 5 for our Ka, the only acid that gives us a Ka anywhere near 10 to the negative 5, if we want 5 as our eventual answer here, is choice C. So remember that relationship between pH and pKa at the half equivalence point. Now 1.8 times 10 to the negative 5 won't give me a pKa of exactly 5. It'll be just a little bit below 5. It'll be 4. I don't remember what, 6, something like that. But it'll be the closest one of the bunch. So in our 4 choices, just sort of a sidebar, the pKa values out of these, the pH of the buffers for each of these, would be somewhere in the range of about 2, or about 1 to 2. This one would give us a pH as a buffer in the neighborhood of 2 to 3. This one would give us a pH as a buffer in the neighborhood of 7 to 8. And this one, the one that we chose, would give us a pH in the range of 4 to 5. So the number on the top end of our pH range is going to be the power that you see there on the 10 to the negative x. That x becomes the top end of our buffer range. So each of those 4, as we do a log or apply a log to that inverse log to that Ka value, would give us a pH range approximately as you see here. And the one that we're looking for then would be the one that choice C gives us in that 4 to 5 range. Question 8 asks about this term of being amphoteric. So the idea that the substance can act as both an acid and a base. So a substance that can act as both an acid and a base. In our case in AP, we're most concerned about acid and base definitions, typically under the Bronsted-Lowry definitions. So it can be both a hydrogen donor, that's an acid, and it can be a hydrogen ion acceptor or receiver. And so it's a compound then that can do both jobs, an acid's job and a base's job. And we should be able to come up with an equation relatively easily to do that. Well, if we look at letter A, that is the hydrogen ion. So hydrogen ion can't act necessarily as an acid or a base. It's the ion that we're most interested in. And it's not a particularly straightforward ion to sort of talk about as its own thing. It's the consequence of a lot of things in our unit, but it's not going to be something that's going to act as an acid and a base necessarily. But if we look at these other 3 choices, we can see that H2CO3 is clearly an acid. It has 2 hydrogens potentially to donate. We can imagine it donating 1 and forming a hydrogen ion and HCO3. Okay. But it's not likely to take another hydrogen ion because it's already neutral. Remember, our bases in this unit, our Bronsted-Lowry bases, are often compounds that have an NH2 on them or a nitrogen somewhere on them because they have that extra pair of electrons with which to form the attraction and the taking or the acceptance of that hydrogen ion that needs a place to sort of dock onto the base. And in the case of H2CO3, there isn't anything like that there. We can't really draw it that way. But if we look at something like HCO3 on choice C, we can see that for this acid, that was the conjugate base. But we could also imagine HCO3 then donating another hydrogen and becoming carbonate, our CO3 ion with a -2 charge. And here then this species is acting as an acid, and this is its conjugate base. So notice then right here in the middle here, we've got HCO3 acting as an acid and acting as a base. Now, it's not showing the equation of HCO3 acting as a base, but it's formed as a conjugate base from our original H2CO3, that carbonic acid. And if you had to, you could write an equation to sort of show how that would look, right? HCO3, just real quickly then, HCO3 acting upon water to show how it acts as a base would form OH ions, and it would also form the original carbonic acid. So there's an equation to sort of show how this critter here acts as a base to form the basic species, but also as an acid down there. So we have 2 equations showing how HCO3 can act as both an acid or as a base. That makes it amphoteric. All right. CO3, by the way, can't act as an acid. It could act as a base, obviously. You see it over here. But it can't act as an acid because it doesn't have another hydrogen to give. Number 9 is a great example of another one of these questions where we can do MV. But it also helps to understand the idea that pH scale is logarithmic. To go from pH of 1 to pH of 2, 1 pH unit, remember, means we've diluted it or changed the hydrogen ion concentration by a factor of 10. Okay, 1 pH unit decrease in this case increase. Check that. We've decreased in acidity, but 1 increase in pH unit is equal to a decrease of H3O concentration. Remember, it's less acidic, right? Of 10, a factor of 10, okay, or by 10 times less. So we've diluted it 10 times to go from pH 1 to pH 2. We've watered it down by a factor of 10, which would mean we'd need to take 1 liter to 10 liters total to dilute it by a factor of 10. 1 liter of the original solution at pH equals 1. If we dilute that with water to 10 liters, it'll have pH equals 2. And to get from 1 liter to 10 liters, we'd need to add 9 liters of water. So D is our answer. By the way, if we added from 10, if we added another 90, we'd have diluted it. Added another 90 to make 100 liters total. We'd have diluted it another factor of 10, and that would make it pH equals 3. And you get the idea. If we keep going, dilute it to 1,000 liters, we'd get pH equals 4. So every pH unit is worth a 10 times dilution, or if you're going the other way, a 10 times increase in a concentration for our hydrogen ions there. For number 10, 1 molar solution of a very weak monoprotic acid is a pH of 5. What's the value of Ka? It helps here to think about, when you're finding Ka, to think about the expression. And for a Ka expression, for any acid, remember our hydrogen in front of the acid, generically then, since we don't have a formula here, we'd have this as our equation for the acid's sort of dissociation for a general weak acid. And the word monoprotic there tells us it's a 1-to-1. So for our Ka expression, we'd have hydrogen ion, right, times our conjugate base over our acid. If it's got a pH of 5, remember, means that we need to take 10 to the negative 5 would be our hydrogen concentration. Remember, 10 to the negative pH is our hydrogen ion concentration. So 10 to the negative 5 is our hydrogen concentration. If we think about this in a rice table, we're going to enter that here as 10 to the negative 5. But it's also going to be the concentration of our conjugate base, because those are formed in a 1-to-1 ratio at the same rate, one at a time, one of each. And in the bottom, we're going to have a 1 molar solution of our acid. And since it's very weak, that means that the X is negligible when we take it away from that 1 molar solution. So essentially, this is still 1. So we have 10 to the negative 5 squared over 1. And 10 to the negative 5 squared, of course, is 10 to the negative 10. So our answer there is A. What do we need to take out of this? We need to think about what is the expression. We can't just jump in and see that 5 and dive in and choose choice C. That's the option a lot of folks would take. Think about a rice table. If you need to write it out, great. But otherwise, recognizing this is the key, that part that kind of would be the linchpin. Do you know that when the pH is 5, that means the hydrogen ion concentration, 10 to the negative pH, is then 10 to the negative 5. And then plug that into both positions on the top of that Ka expression. Couple important things there. Value of Ka for HSO4 ion is 1 times 10 to the negative 2. What's the value of Kb for SO4? Of course, we need to recognize that this is the acid, HSO4. It's acting as an acid. We have a Ka value. So HSO4 ion is going to turn into hydrogen ion because it's an acid, and sulfate as its conjugate base. If this is my acid and this is my conjugate base, to find the Kb value for its conjugate, right, we're going to relate it through that equation that we see on our cheat sheet. Ka times Kb equals Kw, or more importantly, equals 10, or 1 times 10 to the negative 14. Okay? And that means we can kind of work it through there, solving for it from there. We know the Ka value, 1 times 10 to the negative 2. That's given to us. Kb is what we're looking for. Divide that out. Kb is then 1 times 10 to the negative 14 divided by 1 times 10 to the negative 2. Divide that off of both sides. Cancels out. And we end up with 1 times 10 to the negative 12. There's some mental math to do there. You really wouldn't need to write anything out for that one to solve it if you knew those relationships well enough and could kind of do mental math in your head. Super important to be able to relate Ka, Kb, and Kw through this equation as we see it there. All right, let's move on to the next page. Question 13 talks about, 12, talks about the pH of a strong acid solution. Evaluate the acids and bases as you're given them. In this case, it's an acid. It's a strong acid. It's going to dissociate completely. When it does, it's going to give me 0.0001 molar hydrogen ion. It's also going to give me 0.001 molar nitrate ion, but we don't care about that so much because they're asking us to find the pH. And it's this guy that's going to be relevant for that. pH then is inverse log of the hydrogen concentration. Now, it helps to think about this in scientific notation form. That's 1 times 10 to the negative, let's see, I move it over 1, 2, 3, 4 positions. So that's 1 times 10 to the negative 4 molar. pH then is the inverse log of 1 times 10 to the negative 4. And that's 4. Okay, remember that. I should say inverse log. So anytime we do that, then inverse log of 10 to the negative x will be x. That's just math. That's just a math truth. Inverse log of 10 to the negative x gives you x. So in this case, inverse log of 10 to the negative 4 gives us a pH of 4. Boom. Done. Strong acid makes that one short, sweet, and home to eat. All right, let's look at the next 3. Conjugate acid of a weak base. The 4 choices that they gave us up here, the only one that I see in that group that just stands out to me as an acid right away is letter D. I should see that not only as an acid, but one of my strong acids. If I look at the rest of them, they don't have an instant connection to me necessarily. We see NH4 a lot, and you might look at NH4 and recognize what it is as far as its acid or base character. But let's talk about the questions here. Which of these would be classified as the conjugate acid of a weak base? Well, thinking about where these came from, HBr came from Br came from HBr. S, the sulfide ion, came from H2S. I guess. You can even say it came from the bisulfide ion HS. But if we trace its roots back a little bit further, it comes from H2S. Both of those are acids. HBr, a strong acid, and H2S, a very weak acid. NH4 doesn't come from an acid. NH4 comes from NH3. And if it helps, think about the equation for that. NH3 plus water makes NH4, the ion in question, and OH, the other guy. So NH3 then is a base, and NH4 is the conjugate acid of that base. Okay, so question 13, which would be classified as the conjugate acid of a weak base? That's got to be C. We can see it from that equation. Which of these would be classified, number 14, as the conjugate base of a strong acid? Well, here's our strong acid. This is strong acid. So this is a conjugate base of that strong acid. Therefore, A is our answer for 14. And 15, which would be classified as a weak acid, just as it's written here. Okay, which of these 4 things would be classified as a weak acid, right? Well, we've already identified D as a strong acid, so it's not D. We've already identified the other 2 here, both bromine or bromide ion in A and the sulfide ion in B, as the conjugates from acids. So these are both conjugate bases. This and this are both conjugate bases from a strong and a weak acid, respectively, but they're both conjugate bases. So they wouldn't be weak acids. Can we see then that in letter C, NH4 is a weak acid? Well, sure, it's a conjugate acid. It's certainly not a strong acid because we know that list very well, so it would have to be a weak acid. So we actually use C twice here on this set of choices, and that's okay to do too. All right, let's go on to the next page. Question 16. We have a solution containing equal molar amounts of NH4Cl and NH3. Look at those pairs. In a lot of these questions, when you're given a set where a solution contains 2 different species pre-mixed into the solution, it's often the case that you're talking about a buffer. And here we can see that it is. This is a base, and this is its conjugate acid. Remember, nitrogen-containing compounds like NH3 often act as bases. And when we see these NH3s, we see NH2 on the end of a lot of our bases. Here it stands out. I want you to be seeing NH3 because you're going to see it here and there and know instantly that it's a base. And its conjugate acid, we just saw it in the previous question, is NH4. We have then in this solution a base and its conjugate acid. And more than that, we have them in equal molar amounts. But this is a buffer. Okay. Not only do we have them both in equal molar amounts, which means this is not only a buffer, but it's like the ideal buffer, which contains equal moles of both. And that's what we've got here. We're going to come along and add 10 milliliters of water to this solution. Which statement describes the effect of the added water? Key is, with acid-base buffers, to remember that buffers aren't susceptible to pH change by dilution. And the reason is that a buffer's strength, a buffer's pH, is really an effect of its acid to base ratio. The pH of a buffer's pH, and this is a truth in general, no matter what we're talking about, a base with its conjugate acid, an acid with its conjugate base, either way, a buffer's pH is a function, is based on the ratio between acid and base molarities, or the number of moles present. That one would be even better here. It's based on that ratio. And if we add water to this solution, we're going to decrease the molarity of both, right? We're watering it down slightly. So when we water it down, the acid molarity will decrease, the base molarity will decrease, but they're both going to decrease equally. And so the proportion or the ratio of those two stays the same. Therefore, the pH of the buffer stays the same. pH remains unchanged because both are being diluted equally. And if you think about that ratio as being moles of acid over moles of base, which is also valid for buffers and understanding the ratio there, by adding water, you haven't changed the moles of acid or moles of base at all, right? Those haven't changed at all. You've decreased their molarities, which doesn't matter. You haven't changed their moles. Therefore, the pH is going to stay exactly the same. All right, 17, 18, 19. I like these questions to make you think about the concepts of acid-base. I would say, and I think I've read from a few other experts in this, I shouldn't say other experts, a few experts, unlike myself, who doesn't know all the truths that there is to know, that there aren't going to be very often questions like this where they give you a series of choices to use on a series of answers on the actual exam. But it is a good way for us to present you with a few good distractors and do it in an efficient space. So 17, which of the above is most closely related to the distinction between strong acids and weak acids? In other words, what's the difference between a strong acid and a weak acid? And this should be a real basic idea. Basic isn't the right word. This should be a really straightforward, general kind of idea that you already know. This should be common sense for us. A strong acid means we've got 100% dissociation. The acid splits completely. And the weak acid is far less than 100% dissociation. Usually it's in the neighborhood of 1, 2, 3%, or even less than 1%. So strong and weak acids, the difference between them is how much do they dissociate? How much do the ions come apart when that acid enters water? And so that's C, the extent of the dissociation of the electrolytes, the ions. How much do the ions come apart? 18, which of the above is most closely related to the distinction between concentrated and dilute acid solutions? And this is true whether we're talking about an acid, a base, a salt. Concentrated means you have many moles per liter or more moles per liter compared to a dilute solution where we have fewer moles per liter. And the way that happens, of course, is we water it down. We increase the liters while the moles stay the same. And when you have fewer, or rather equal number of moles, but in a greater volume, you've diluted the solution down. So that moles to liter amount decreases in a dilute acid. Therefore, the number of moles present per liter, letter A, is the choice. The difference between those is the difference between concentrated and dilute acids. And finally, 19, which of the above accounts for a pH of 2 for 0.001 molar HCl, but a pH of 4 for 0.0001 molar HCl? Look, it's HCl in both, right? So the identity of the acid doesn't matter. But it is important to note here that HCl is a strong acid. So in both of these solutions, it'd be completely dissociated. Therefore, choice C cannot be the answer because they're both strong acids. In both solutions, the ions would be completely dissociated. So C's out. Okay. The difference between these, what's the difference? These are two different molarities. And this takes us back to the previous choice, moles per liter. This one has 0.01 moles for every liter. This one has 0.0001 moles for every liter. Moles of what? Moles of H, right? Moles of hydrogen. Moles of hydrogen ion per liter. Moles of hydrogen ion per liter. Because it's a strong acid and it's dissociating completely. So the difference between these is the number of moles per liter again. And A pops up once again. Okay. By the way, letter B mentions this term molality. Molality isn't necessarily something that we see anymore in the AP curriculum. When it pops up in here, it's probably in an older question. It used to be part of things that we looked at with colligative properties, which have to do with why ice melts when you throw salt on it in the wintertime. But that's a concept that's been taken out of the AP curriculum in recent years. So you wouldn't expect to ever have to bump into the word molality, which is not the same as molarity. That much is pretty important to note. All right, let's look at 20. We're diluting an acid. We're adding water to an acid solution. That's diluting it. The word dilution is not here. So we need to understand that that's what's happening. When you add water to a solution, you're watering it down. That screams adding water. That screams dilution. And when you see dilution and not a whole lot else going on here, just adding water to it, you want to go to our dilution equation. M1V1 equals M2V2. Plug in the original molarity and volume. The original molarity was 0.003. The original volume was 100 milliliters. Notice again, I'm doing multiple choice, so I'm going to leave my units off. I want to pay attention that they're the same units, but then I'm going to get rid of them. And then at the end, my molarity, we don't know, but the new volume is going to be what? 200 milliliters of water are added to 100 milliliters. So we don't know M2, but our volume is 300, not 200, but the total sum of those. And at this point, if we divide these out, right, M2 is going to come out to be 0.001. Notice again that we've tripled our volume. Therefore, our molarity here is going to be 1/3 of what it used to be. So triple the volume, cut the molarity by a factor of 3. Gets 3 times weaker. And so it's a 0.001 molar. Now, this is a strong acid again. Remember, right? Nitric acid is a strong acid. So if it's a strong acid at 0.001 molar, that means that this is also the hydrogen ion concentration because it's going to dissociate completely. And the inverse log of this will be our pH. Well, 0.001 is 1 times 10 to the negative 3. And the inverse log of that value is 3. So our answer is A. Okay. All right. Next 3. Which of the above aqueous solutions is an example of a Bronsted-Lowry acid? Remember, that means it's a hydrogen ion donor. It's got hydrogen ions to give. We want to look at those 4 choices like we did with the last ones. Try to identify what we've got here. KOH, hopefully, we recognize is one of our strong bases. So that's definitely not a hydrogen ion donor. It's definitely not an acid. NaHSO4. That looks like a salt, but it does contain HSO4. And HSO4 was mentioned in an earlier question in this very packet, but be that as it may, it has hydrogens in it. And that can react with water to give another hydrogen ion away, give us H3O, and give us the sulfate ion. That's actually a very effective acid particle, the bisulfate or HSO4 ion. So this is an acid. It's not one of our strong acids, so we'll write it as a weak acid. But question 21 says, which of the above solutions is an example of a Bronsted-Lowry acid, a hydrogen donor? Well, boom, we found it, right? Because the HSO4 ion from that compound there in choice B would act as a hydrogen donor by the equation that we've written. So 21, got to be B. Okay. Which of the above aqueous solutions would be classified as neither a Bronsted-Lowry acid nor base? In other words, something that can't donate a hydrogen, but also can't accept a hydrogen. Well, we definitely know that it's not our base. That's a base. We know it's not B. That's an acid. What about D? NH3 we've seen a lot. We've written the equation for NH3 quite a bit. NH3 likes to get with water as a base because it accepts or takes a hydrogen from the water to produce NH4 ion and that OH. Again, that's that proof that it's acting as a base. So here it's acting as a hydrogen acceptor. That makes it a Bronsted-Lowry base. So D's out as well. But why is C neither an acid nor a base? It's a little bit trivial, but C2H5OH is actually ethanol. That's an alcohol. C2H5OH isn't going to act as an acid, isn't going to act as a base. It's an organic alcohol compound. Now, it sure is deceptive of them to throw that C2H5OH in there and make you think, OH, 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 it's got to be a base. But it's not. Now, we get into some of our stuff with structure that we've looked at briefly. We haven't looked a ton at it this year. But we look at our structure of C2H5. There that is. There's C2H5. OH is sort of that right there. And you might be looking at that and thinking, wait a second now. I can see then maybe why it's not a compound that would act to receive a hydrogen, because I don't see any nitrogens in there any place or that kind of thing. But how come it doesn't give off an H? Why doesn't it maybe lose that last H on the right? We have seen ions. We have seen organic acids that will donate a hydrogen. So how do we know this one won't? I'll just kind of give you a bit of sort of a red flag to look for. A structure that acts as an acid, an organic compound, remember that means containing carbon in there somewhere, that's going to act as an acid. Typically their formulas will include a COOH in the structure or a CO2H in the structure. Or it might be an acid that starts with hydrogen in the beginning, actually, like citric acid has H3 out in front, and then it has the big organic structure behind it, C6H5O7. In that case, it's a carbon-based organic compound that has some hydrogens in it that it can't lose, those 5, but it also has these 3 hydrogens out in front that can be lost as hydrogens, one at a time, and that makes this an acid because there are 3 hydrogens that can be lost. On the COOH, that hydrogen can also be lost. Same thing here. So be on the lookout for those. I would think that a question like 22 or 23 rather, 22, and asking you to recognize that this is an alcohol wouldn't be necessarily something that you'd be expected to see, but you will see plenty of organic compounds with carbon in them that are going to act as acids. So be on the lookout and don't be too quick on the trigger to say that can't be an acid or that can be an acid. Don't expect to be deceived, but be on your guard. Which of the above solutions would have the highest pH? We're looking for a good base, right? And a high pH means a good base. That's got to be A because that's a strong base. All right, hitting the end here. 24. It's describing to you a lab scenario. A student pipettes 25 milliliter samples of hydrochloric acid into separate flasks. So you had 4 different samples for 4 trials. Adds to the acid 20 milliliters of water. And then add 3 drops of phenolphthalein, which is that colored indicator. Remember, changes color when we reach the equivalence point. Phenolphthalein changes color at a pH that works real well for a strong acid, strong base titration, and that's what we're doing here. It turns pink, as it mentions, when the equivalence point is reached. They don't ever mention equivalence point, so they're kind of hoping that you'll know here that when that color shows up, pale pink color persists, that means we've reached the equivalence point and the titration is done. It took, it says here, 32.25 and then 3350, 3349, 3351. Look at those 4 choices there. One of these things is not like the other, right? This is really low compared to the others. The other 3 are basically identical. What's up with that one? In other words, in trial 1, it took a lower amount or a smaller, lesser amount of NaOH to get to the equivalence point. What does that mean? It means it took fewer moles of base. Fewer base moles were needed to reach the equivalence point. What does that mean? Keep zooming in here. If there are fewer base moles needed to reach the equivalence point, that means there were fewer there were fewer acid moles present at the beginning. Fewer acid moles in the original sample that was taken at the beginning of that trial. So what happened in trial 1 that didn't happen in trials 2, 3, and 4, which seem to be very consistent? Let's look at those choices. Choice A says the student added too little phenolphthalein to the first solution. It says he added 3 drops, or she added 3 drops to each one, so that probably isn't the case. Plus, I'm here to tell you, you'll see a nice pink color whether you use 1 drop or 5. Okay, 3 drops, 1, 5, probably wouldn't make a lot of difference. B, a different amount of water was added to the first flask. Well, it says here that wasn't the case. 20 milliliters of distilled water were added to each one. That was probably not the case either. It says the burette was not rinsed with sodium hydroxide solution before filling. Now, D actually talks about rinsing as well. Rinsing is the theme in both C and D, and those are our two choices right now. So what does that rinsing accomplish? Well, think about it. If you have a glass that you used for water the night before, and or an hour ago, you drank some water out of it, you've drank most of the water, it's empty, but there's that little bit of water that's still at the bottom of the cup, right? Now you come behind and you use that cup again, except now you pour into it something else. You pour into it, say, root beer. And if you do that, the root beer is going to be slightly watered down by the water that was left behind from your previous drink, right? So by not rinsing it out, now this is weird, you wouldn't do this in your kitchen, but imagine if you didn't want that little water in there, you could dry it out with a towel like a sane person. But a chemist might be tempted to pour a little bit of root beer in there, swish it around with the hopes that the root beer will pick up that water that was in there and then dump that down the drain. And then what's left behind in your cup? Basically root beer, right? You've rinsed out the water by mixing it in with some root beer and dumping it out. And if now you add root beer to that cup, there wouldn't be any water really left behind to dilute your root beer. So we rinse our containers in a titration. We rinse our burette, we rinse our pipette with the solution that you're going to dispense from that burette or pipette. We rinse that beforehand and we dump those contents down the drain. And we do that to make sure that there's no carryover water left from before. So which of these two, C or D, would reduce the acid moles? In other words, which of these two would water down the acid and give us fewer acid moles than we thought were there? Well, which of these would water down the acid? D, because there might have been water left behind in that pipette. And if there was, when you thought you had 25 milliliters of acid in that first sample, there was actually about 24.5 milliliters of water, or rather 24.5 milliliters of acid and a little bit of water, and that little bit of water diluted it down. And that means there were fewer acid moles than you thought, and there was less base needed to neutralize them. Always run and rinse that out, and not doing so will reduce the moles that are actually present in the sample that you've measured out. All right. 25, 6, 7, another group of questions here. Which would have the lowest pH? Which of these is the best acid? Which is the best base? That's kind of what we're looking to understand with these questions. What do we got here? 0.1 molar NaOH. That's going to be a strong base. It's going to have a high pH. That's not our answer for 25. Sodium chloride, what's that? Sodium comes from a strong base, sodium hydroxide. Chloride, right, comes from a strong acid, hydrochloric acid. If you have in our compound here sodium from a strong base and chloride from a strong acid, strong base, that's a tie. That makes this a neutral salt. Neither one of these parts, sodium nor chloride, can act as a base or an acid in solution, and so neutral salt. But if we look at letter C, we have sodium acetate. Sodium comes from a strong base, sodium hydroxide. Acetate is the conjugate base from a weak acid, acetic acid. Sodium from a strong base, acetate from a weak acid means this will be a basic salt. And we can write the equation to show that, but that acetate ion would act as a base. Sodium can't do really anything as far as acting as an acid or a base. What about the last one? Aluminum chloride. We know chloride comes from a strong acid, and aluminum comes from a weak base. Aluminum, for example, aluminum hydroxide, is not a strong base, so it must be a weak base. Therefore, from a weak base, from a strong acid, that makes this a slightly acidic salt. So we have four very different compounds here: a strong base, a neutral salt, a basic salt, and acidic salt. Which of these will give us a low pH? Which of these will act as an acid? Well, it's got to be D, right? It's an acidic salt. Which solution would have a pH closest to pH equal 8.2? That's not neutral, so it's not B. That's not a real high base, right? It's a slight base. So it's not going to be the result of a strong base like sodium hydroxide. And not only is that a strong base up there in choice A, it's also a pretty strong concentration. 0.1 molar is a pretty decent concentration. So this pH must be coming from something that's a base, but not too much of a base. That's got to be our basic salt. That's C. And then which solution's pH will remain the same if 50 milliliters of distilled water is added to each. Remember back we talked about buffers. Buffers, when you add water, their pH doesn't change. We don't really have a buffer here. We don't really have a buffer in any one of these four. But pH is unaffected when you add water to buffers. It's also unaffected when you add water to neutral salt solutions. It just so happens that letter B is a neutral salt solution. Watering down salt water won't change its pH. Adding water doesn't change the fact that sodium can't act as an acid and chloride can't act as a base. They both came as the conjugates from strong base and strong acid, respectively. And so neither of them can act effectively as a conjugate base or acid. Therefore, adding more water won't change that. The pH will remain exactly the same. Last page. If the dissociation of water is endothermic, we see that equation there, and some room temperature water is heated to boiling, which of the following is true? This throws us back to last unit where we had to talk about equilibrium and shifts, like Le Chatelier's principle. What will this do? What does endothermic do? What is it favored or is it discouraged? If we're increasing the temperature by raising the temperature to boiling, and this reaction is endothermic, endothermic means raising the temp. The forward reaction, if I could spell forward, the forward is favored. So what? If we increase the temperature, we're going to get more of these, we're going to get more of these, and we're going to get more of both, really, right? The forward reaction is favored because this is endothermic and we're raising the temp. Okay, so let's look at our choices. Which of these will be true? Letter A, the pH will be 7 and the solution will be acidic. Now, wait a second. pH 7 means that the hydrogen ion concentration is 1 times 10 to the negative 7. That's the case at 25 Celsius. If the pH will be 7 in choice A, that can't be the case any longer because, remember, we increased this and we increased this. So at room temperature, the pH was 7. But now we've increased both the hydrogen ion and the hydroxide ion. So the concentration of hydrogen ion would no longer be this at boiling point at 100 degrees Celsius. It's not equal to that anymore. It's going to be greater than that. It's going to be maybe 1 times, let's say, 10 to the negative 6, just for another number. It's going to be greater. So it can't be that the pH is 7. That doesn't work. The pH will be greater than 7. Hold on a second. If pH is greater than 7, that would mean that this number would have had to decrease. pH greater than 7, no. Here our pH will be, so let's, for our example, pH would be 6 at 100 degrees Celsius. This is just a number we picked, right? Because again, remember, hydrogen ion increased, so I increased it, wrote this value here, and I just picked a number to make our math easy. And I increased it there, so the pH is actually going to be 6. It's not going to be greater than 7. It's going to be less than 7. So that's out. I didn't even read the rest of that choice because it's not true. pH will be less than 7. pH will be less than 7. So C and D are both okay. The solution will be neutral. What does neutral mean to us? Okay. This is a good chance to disparage a rumor. Okay. It might be bumping around in your head. Neutral, pH neutral, in our solutions here, does not mean pH equals 7. You're like, wait a second, you've always said pH 7 is neutral. pH 7 is neutral at room temperature. But it's not because it's 7. It's because at pH 7, the two concentrations are equal. The two concentrations of hydrogen ion and hydroxide ion, the acid species and the base species, are equal. That's what pH neutral means. It doesn't mean that pH has to be 7. It means those two things have to be equal. And it turns out that pH 7 for room temperature is our neutral condition. But look at our situation here. Are the hydrogen ion and hydroxide ions going to be equal in concentration under these new conditions? Yes, right? Because look, endothermic favored the forward reaction, but it increased both of these. It increased both of them equally. And so they've both increased. If this is 1 times 10 to the negative 6, for example, this also then would have to be 1 times 10 to the negative 6. The pH would be 6. under that circumstance. And the pOH would actually be 6 too. And like, wait a second, they'd have to add up to 14? They don't have to add up to 14 if we're not at room temperature. And nearly always we are. This question is a bit of a curveball, but it's a fair one because it throws us back to some stuff from our previous unit and makes us prove that we know what the heck we're talking about when it comes to pH and acid-base chemistry. So it turns out that at higher temperatures, pH and pOH don't add up to 14, they add up to something less. And at colder temperatures, in theory, they'd add up to something more. So C, pH will be less than 7. Yep, it's about 6 by our kind of goofy estimations. The solution will still be neutral. Yep, it will, because H and OH remain equal to each other. Choice D says the solution will be acidic, right? pOH will be less than 7. That's true, but it won't necessarily be that it's acidic under those conditions. Okay? As long as those two things are still equal, it's not an acid, it's not a base, it's a neutral solution. That's a pretty important idea to be able to pull out, okay, as we're looking at some of these questions, and understanding what neutral what neutral means with respect to pH and what it doesn't mean as well. 29. We've titrated the acid, it says here, a 20 milliliter sample, titrated to the endpoint, and that, to do so requires 50 milliliters of the base. Okay. Now, after the first 30 milliliters were added, so that would be before the equivalence point, the pH of the solution is 5. Now, it helps to visualize, I think, a little bit, our titration curve again. Something like this. They're saying that this is found at 50 milliliters, the equivalence point. That would make us, let's see, the half equivalence would be kind of here at around 25 milliliters. And in this case, they've added 30 milliliters of KOH being added. So we're right about here, let's just say. And it says the pH of the solution is 5. Okay, so I'm going to dash that across and say pH equals 5. So this is kind of just a quick graphical description of what this question is saying. At around 30 milliliters, pH equals 5. What is the dissociation constant? Let's set up the equation, expression. Ka equals, for HX as our acid, we'd have hydrogen ion, we'd have X ion, our conjugate base, and we'd have HX. Which of these do we know? Well, we know pH 5, pH of the solution is equal to 5. That means that the hydrogen ion is equal to 10 to the negative 5. So I can fill that in, 10 to the negative 5. Or if you're more comfortable, 1 times 10 to the negative 5. Okay. What else do I know? I haven't, let's see, have I got acid and base at this point in the titration? Yes. At this point along the way in my curve, I'm going to have both acid and base. I've got, let's see, which do I have more of? I'm past the half equivalence point. So at this moment of 30 milliliters being added, I have a little bit more base and a little bit less acid, right? Because we've gone past the half equivalence point. We have a little bit more of our base and a little bit less of our original acid. So what's the proportion? If it took 50 milliliters to titrate the solution and we've added 30, think about that as a fraction. You've added 3/5 of what would be needed to reach the equivalence point. You've titrated 3/5 of the acid. In other words, you've turned 3/5 of the original acid into its conjugate base. And so my conjugate base is now 3/5 of the particles in that solution. And my original acid is now 2/5 of the original acid that was in that solution. 2/5 remain as acid. The other 3/5 have been converted to conjugate base. So I don't even know what those numbers are, but I can plug in there a fraction, and that's going to let me finish this problem out real nicely. Because if I simplify this down, that's basically 10 to the negative 5, right, times 3 over 2, which is what? That's 1.5 times 10 to the negative 5. Look at that. 3 halves is 1.5. 10 to the negative 5 is 10 to the negative 5. And booyah, we got that answer right there. That's kind of a quick way to do it, recognizing that we've turned some of our acid into base and being able to do a quick fractional on that. You could do it a little bit more mathematically, but if you can find that route, it's going to be the one that's going to get you there. Helps to understand where we are along the curve and maybe to diagram it for yourself. If you can do it real quick and messy, it doesn't have to be fancy for a multiple choice question. Last 2 questions. All right. Selecting the answers below. What would our pH be? This is a strong acid, right? So in a 1 molar solution of a strong acid, we're going to get 1 molar solution of hydrogen ions. It's going to dissociate fully. Now, to get the pH, we need the pH of this value. How do we write 1 as a power of 10? 1 is 1 times 10 to the 0, right? So if I do inverse log of 1 times 10 to the 0, that's going to be 0. pH is going to be 0 here. 1 times 10 to the 0, if we do the inverse log of that, we get 0. Remember, inverse log of 1 times 10 to the negative x equals x. That's just math. And in this case, then, the negative log of 1 times 10 to the 0 would be 0. And that would be our choice A, then, as our answer. What about this one? This is a strong base. This is going to give me a 0.01 molar OH concentration, acting as a base. From that, I can find my POH, right? Because POH, again, is the inverse log of our hydroxide concentration, which is this guy right here. Well, what is that answer? That's 1 times 10 to the negative 2, right? That's what that is. So the inverse log of 1 times 10 to the negative 2 would be 2. POH, then, is 2. Now, that's not the answer. Don't go up there and circle choice C. They want pH. So remember, pH is 14 minus POH. So that's 14 minus 2. That's 12. So our answer here would be D. Okay. So, man, tons and tons of things on these multiple choice questions. Thanks so much for listening into them, following along with us as we go. And if you have other questions, please feel free to see me one-on-one. Glad to help you.